more than a feeling, more than a feeling, more than a feeling. I'm a song, more than a feeling. I make it dreaming, more than a feeling. I see my Marion walking away. All right. Okay, good. So it's a beautiful, beautiful morning. I'm feeling amazing. Okay, so since I got the mic and I got the free day, I had to do this weird thing. Look, I had this cable. You learn something new every day. All right, this went to my laptop's power supply. Apparently, this is called a Mickey Mouse plug or some weird specification name, but in any case, this one's actually only rated for 2.5 amps at 125 volts. Anyways, I went downstairs and I found a new one because this housing was breaking. And, you know, on the main side, if it was on the other side, like, I don't, but, you know, I don't really want to play with the mains. So I'm going to probably toss this. You know, like, I could cut it and resolder a new housing on it, but it's like, do I really want to do that? Especially because the replacement costs $6. Okay. Not even worth the time or the breath. Okay, here we go. So yesterday, we learned about Faraday's law. Now, Faraday's law, I was thinking about, is definitely the weirdest of the, let's say, which Maxwell's equation is the hardest to conceptually understand? Integral form only. Because I don't know the differential stuff. We didn't, that's not in our class. I knew it. Because here's why Faraday's law is so weird. It relates the time derivative of a magnetic flux to a closed line integral, weighted by the E field. So I think maybe one thing to understand here is imagine that the flux here was over a closed surface. Well, then you can already know that the time derivative is zero because Gauss's law, which is another Maxwell's equation, says that the magnetic flux through any closed surface is zero. So if it's always zero, then there is literally nothing you can do to create a net flux through that surface. But however, let's say that the Gaussian surface is not closed. Well, actually, I don't know. Are Gaussian surfaces always considered closed? Yeah, so I think that they are always closed. Yeah, so by definition, so what I'm saying is, let's say that your surface is not closed. Well, then there's nothing imposing that the flux to be zero. So now, imagine that we change the magnetic flux through some area, through some surface. In Faraday's law is the curve, the closed curve traced by dl, the boundary of the surface used for the magnetic flux. Okay, in Faraday's law, the closed curve you integrate around is the boundary of the surface used for the magnetic flux. Okay. Which makes sense. Like, how could it be anything else? The surface is not unique. Many different surfaces have the same boundary curve. Oh, interesting. So if C is a circle, it could be a bulging soap bubble. Okay. Um. So in the circle case, if we pick the bubble, more area versus the disk, is the flux change should be the same, since the E line integral has to be the same. Actually, maybe I'm wrong. I can't. Oh, okay. For a given boundary curve, the change in magnetic flux has to be the same for any surface spanning that curve. Otherwise, Faraday's law would be ambiguous. Oh, so you could think of it as like this is the thing that you start with, or let's say, okay, for any closed E line integral, um, yeah. This is so cool. So for any closed line integral of the electric field, it must be that the. Oh wait, hold on. I'm glad I remembered now and not 2 hours from now. Okay. That's kind of embarrassing. So here, I think I understand what's happening. Okay, we turn off the current, and the B field into the page is decreasing. Now, it creates an electric field that is going to try to maintain that B field. Now, the E field is going to cause the charge to move, which is a current. So the charge is moving, and that is a current. That current, if it's, for me, clockwise, looking at it from the same perspective that we've been drawing, will make the B field into the page. So it has to be clockwise. So the E field is going to be clockwise, which, how do I turn? Oh yeah, wait, I need to take the derivative, and then I need to radial, counterclockwise tangent, clockwise tangent is the negative of that. Oh yeah, because cos goes negative, but sine. Oh wait. If theta is 0, okay. All right, so E is going to be. So first we're going to take dr d theta is equal to minus r sine theta r cos theta. Now the tangent, so this is counter clock tangent. So to go clockwise is just -1 times this. So we're gonna get r sine theta minus r cos theta 0. And this is going to be the direction. This is the direction of the E field. But actually, okay, the direction of the E field, I don't know if it's going to have the R. Maybe it's just. But we now know the direction of it. So this is actually E hat. E hat. Okay, we got E hat. E hat, hat denoting a normed vector. A vector with magnitude 1. Okay. Let me just pull this up here. All right. Yeah, bro. Sorry I was on mute. All right, I'm not on mute anymore. All right. So, all right, so we got this. But now, okay, so but if we have E hat, then we will be able to find the determinant. So we can pull out the dq. So dq integral r vector cross E hat times the magnitude of E. So E vector is equal to E hat times E, which is the magnitude. Okay, so we're going to do, d tau, or tau is equal to the integral of E times dq times the integral of r vector cross E hat. So now we can take the cross product. We're going to get r cos theta, r sine theta, 0. And then the E hat is sine theta minus cos theta, 0. All right, we take the cross product. All right, I and j are 0. So k hat times minus r cos squared minus r sine squared. So we're going to get, minus r times 1. So minus r is, okay, so that's it. So the torque is equal to, oh wait, but dq can't be taken out of the integral. What am I talking about? Oh, yeah, dq can't be taken out of the integral, but r cross e after evaluated can be. Okay, I get it. So, so you can't really do this. So it's going to be tau is equal to e times minus r times the integral of dq. So is equal to minus q e r. That's the torque. All right, so since we found the torque, we can now relate it to that change in angular velocity, which is what we're trying to find. So minus q e r. I think the minus sign might be a mistake, but I don't know. Is equal to the rotational inertia mass times the radius squared, which is actually just only for the ring. Okay, then the final angular velocity, the initial angular velocity is 0. So we can just do omega sub final over delta t. So we can find that the E field, or wait, do we have a direction on this? I think that this is scalar. So now we're just relating the magnitude of the torque to find the E field. Okay, so E is equal to mr omega final over delta t minus q. Delta t times q. Okay, so this is the E field. Now, we can go back to the closed line integral, and we're just going to get E times 2 pi little r is equal to, okay, so now E times 2 pi little r is equal to mu 0 I n times pi big R squared over delta t. So now E on this side is equal to mu 0 I n pi r squared, and then the pi's cancel, and you just get left with 2r delta t. And now we can solve for this. So we solve for this. Minus mr omega final over delta t q is equal to mu 0 I n pi or big R squared over 2 little r delta t. Delta t's cancel. Okay, so the omega final is equal to minus mu 0 I n pi big R squared q over 2m little r squared. Let's see, did I get it right? I guess I did. The only thing is that okay, so let me write up my solution. And then my solution will be this like really long-winded thing just to like prove that if you do it the long way that you get the same answer. Okay. So because of I guess Lenz's law, the change in the magnetic okay, wait, so answer. The change in the magnetic flux will produce an E field that will move charges in a way so as to produce a current that will maintain or maintain the original B field or counteract the change. Therefore, okay, so this is for the first part. Therefore, the field lines, or wait, will be clockwise, and the ring will move clockwise. This current will make a B field into the page minus K hat. Good. Now, okay, wait, but I did want to ask something else. So Faraday's law doesn't exactly say that the K hat direction is 0, just that since it's perpendicular, it's not going to influence that dot product. But it still could be non-zero in reality, right? Okay, so I do want to clear that up. Oh, because okay, so the symmetry, yeah, this is what it is. The thing that eliminates K hat is that we could mirror the solenoid across a plane, a perpendicular plane. And well, that's not actually true though. Okay, wait, hold on. Let me read the answer then. That comes from the symmetry of the specific setup and not from just the dot product. For an ideal long solenoid whose magnetic field changes only along the axis direction, the setup is rotationally symmetric about the axis, translationally symmetric about the axis, mirror symmetric in planes containing That's what I thought. I mean, that's what that means. But it's like sometimes you just got to clear up the geometry phrases. Um. Okay, so nothing in the setup that picks a preferred K. There's nothing in the setup that picks a preferred plus K versus minus K direction for the induced electric field. If okay, so if we were to look at the tube, and then we were to make this ring, and let's say we turn it off, and then there's a K hat E field produced. And then we slice this thing. So this is a mirror plane. Wait, but no, wait. If let's say if I draw a circle and this is pointing this way. Okay, yeah, then I mirror this, then this is pointing that way. No, wait, what? If I do this, then it's pointing this way. Okay, so then all right, so that's also if a of course we know Faraday's law says that we get a net, closed line integral of E dot df. But let's say there was a uniform E k hat component. Then In the ideal solenoid problem, everything sourcing the induced field is symmetric under rotations about the axis, translations about the axis, and reflections from z to minus c. Okay, this is what I want to know, though. When the current is off, it's true. But when the current is on, then the solenoid is definitely not symmetric about a z reflection, since the B field and the current's sense are directional, minus z hat, minus k hat. Most importantly, the changing magnetic field is, with no preferred direction along z. I don't know what this means. So if an induced electric field had a uniform axial component, EZ, that would mean the setup had chosen a preferred direction. But also, if we were to cut it this way, okay, so now we're looking at it kind of from the side. This is going to be coming out of the page at the top, and at the bottom it's going into the page. And if we were to reflect it, it's the mirror plane. Then yeah, it has to be the fuck. Okay, I'm gonna say ask in office hours what really is the reason that the k-hat component couldn't be non-zero after the current is turned. But I'm willing to just accept it and just say, okay, the it's azimuthal, and that's it. It's just azimuthal, which is fine. I'm like not hung up on that. Okay, good. All right, so let's write up the solution. Since it will not contribute to the line integral perpendicular, all right, let's go to the next problem. That was that. Oh wait, no, I'm writing up the solution. All right, so how do we write up this solution? Okay, so the first thing to do. So I don't know. There's the problem is there's a lot of components to this problem. Okay, so reasoning about solution. Because we are changing a current, we should immediately think Faraday's. Okay, so Faraday's is C int E dot dl is equal to D minus D flux B over dt. Okay, we apply a finite diff approximation, I guess. I don't know if a finite diff delta. So we're going to get C int E dot dl is equal to minus delta flux B. So I'll just write it out. Delta T. Okay, we are able to find the so let's write this is equal to minus flux final minus flux initial over delta T. Find the initial flux, and the final is 0 as there is no current through. There's no current. Right, because if let's say we wanted to compute the flux, we would use, so draw a solenoid with some wires at the top and the bottom, and then draw a rectangle, as your closed line integral for Ampere's law, which is, closed B dot dl is equal to I enclosed times mu 0, but this is 0, so then, this 0, this 0, this 0. So then, BL is equal to 0, but L is non-zero, so then B is 0. So B has to be 0. You can easily show this with a quick application of of Ampere's law by doing the rectangular closed line integral. So, it's like Cint B dot dl is equal to I enc times mu 0. But I enc equals 0. So then, B times L is equal to 0, but L non-zero implies B equals 0. Okay. So, which implies the flux is 0. Oh wait, does it imply the flux is 0? Yeah. But it doesn't imply the change in flux is 0. Okay, so now we get is equal to flux initial divided by delta T. So is the Cint E dot dl. Now the flux, we can find the flux. So first off, flux I is going to be, we use the solenoid approximation to see that B, magnetic field B is uniform inside equal to mu 0 Ni minus k hat and 0 outside. The flux integral quickly evaluates to B times pi, let's see, wait, hold on. Solenoid current R is radius R. Radius R greater than R, okay. Charge Q, mass M, coaxial solenoid stationary initially, current is turned off, ending, blah, blah. Okay, good. So quickly evaluates to BA is equal to B times 2 pi big R. Okay, so then the flux initial is B, which is mu 0 I n 2 pi R, big R. Wait. Pi R squared. Okay, good. Yeah, because the area. Okay, now we need to find E dot dl. So by the symmetry of the cylinder, E has constant magnitude at a fixed R and is parallel to dl everywhere. Or anti-parallel. Anyways, we get E times 2 pi little r is equal to flux I over delta T. But what is E? So this is kind of the hardest part, I think, to remember about the problem is, okay, so we do tau equals I alpha. How to remember to do this? Anyways, then remember the problem is related to a change in angular velocity. Okay, so tau is equal to I times omega final omega initial equal to 0. Okay, and then tau is equal to R vec cross df. D tau is equal to R vec cross df, which is equal to so basically we're asking what is the torque on the ring given an azimuthal E field. Okay, so this is R vec cross E dq. Okay, so now we take the integral. So tau is equal to int R vec cross E dq. Okay. Oh, what just happened? Oh, I did this fucking thing. Okay. R vec what is R vec in E? Okay, so R so I think I naively just made R little r cos theta, little r sine theta. But okay, so let's do that and see if chat picks up on what might be a mistake. So let's just say R vec is equal to R cos theta R sine theta 0. Then oh wait, no. Yeah, this is R. But what is E? E needs to be thought E hat can be determined through by reasoning about what counteracts the change in magnetic flux. If we cut off the current, the direction of the change in flux will point positive k hat. But imagine, though, that we started spinning the ring of charge Q counterclockwise. This creates a current that makes a magnetic field pointing also out of the page. But we want to oppose the change. Therefore, the E field must be directed azimuthally clockwise to derive the clockwise azimuthal vector. Take take minus dr vec dt. So dr vec, or not dt, d theta. dr vec d theta is equal to minus r sine theta r cos theta 0. So then, so then E hat is equal to sine theta minus cos theta 0. Okay, so now we can do the r cross r vec, and E vec is equal to E hat times E. E is just mag of E vec. All right. All right, so that's pretty good stuff. So the next part about this problem is taking the cross product. So now we find r vec cross E hat. So wait, hold on. First off, let's just rewrite the torque. So tau is equal to int r vec cross E hat E dq is equal to E dq, E int r vec cross E hat dq. Okay, so now let's eval r vec cross E hat. Det of I, J, K, I think is a pretty simple one. This is going to be r cos, r sine 0, then sine minus cos 0. Okay. So it's going to be k hat times minus r cos 2 minus r sine 2 is equal to minus r. Minus k hat times r. So this is the direction of the torque, is minus k hat. I always get confused about the direction of torques. Or I always forget it going this way. If you have the R and F, so, R, F, torque's pointing minus k hat. So yeah, so it's spinning counterclockwise. Or it's spinning, clockwise. Good. With a magnitude of R. So now tau is equal to E, or minus E R k hat integral dq is equal to minus ER minus k hat ER q. All right, so now that we have the torque, we have the torque. So minus k hat ERQ is equal to but what is the direction of the okay, so I guess here is probably where I made my mistake earlier, is what is the direction, because just like angular acceleration is a vector, is angular velocity a vector? It has to be. It's got to be. No, I don't think you're supposed to do this. I think you really have to figure out what the actual direction of the I think. I'm not positive about that reasoning step. But anyways, let's just say that it is. So oh, and then uh there's two eyes in this problem. Actually, it would be fun to do derive this. I messed up on the moment of inertia calculations on my exam. I forgot about center of gravity and I just kind of took the integral and it didn't end up so good for me. Because the thing is, I didn't do dm. I didn't do a mass element. I messed it up. Mm. Oh, wait. No, this is little r. But wait, where did my minus go? Wait, Wait. Okay, that's a great problem. A charge Q is injected into a uniform magnetic field and also in the same region of space a uniform electric field. The value of the charge's initial velocity The value of the charge's initial velocity when just entering the region, okay, is given. The magnetic field is given and the electric field is given. Well, the magnetic field makes the charge move in a circle. The charge also moves such that its path forms a helix. But because of the presence of the electric field, the helix becomes stretched along its axis. In the time... Okay. All right. I get it. Okay, so this is problem 4. Right? 4? Wait, where did I get 4 from? What the hell was that about? That was weird. It's not 4, it's 32. Okay, so, all right, so all we need to write down is, VI equals VX, VY, VZ. Then the magnetic field B is equal to B minus K hat. And E is equal to E I hat. Okay, good. So now what we want is, we want to know, find delta X in T time. All right, so the first thing we want to do is we want to find FB is equal to the determinant IJK, then VX, VY, VZ, then 0, 0 minus B. So I, it's going to be I hat times minus B VY minus J hat times minus B VX. The plus cancel. Okay, this is going to be equal to minus B Vy in the X direction and B Vx in the Y direction. Okay. But really, I mean, the thing is, it's B. So, QB times minus VY I hat plus VX J hat is equal to FB. So this is the, and wait, and we have a vector. Now what we want to do is say that, F equals ma, Newton's second law, where the system is the charge q, and we want to say for centripetal, so let v perpendicular be to the norm of, let's just do this. Because let's just take the norm of FB. So the norm of the magnetic force let's just do this the long way just so that I get it. So it's going to be minus QB VY QB VX. Okay, so it's going to be, you know, Q squared B squared VY squared plus Q squared B squared VX squared square rooted. So we can factor out, you know, Q squared B squared times square root of, or times VY squared plus VX squared square rooted. So then we're going to get QB, you know, QB V perpendicular. Okay, good. So now QB V perpendicular is equal to MV perpendicular squared over R. Cancel the V's. Then the radius R is equal to MV perp over QB. Now we have the radius. Now what we want to know is that in this, with this velocity, V times V perp times T, which we'll call the period. So this is the period. So the period times the velocity is going to be equal to the circumference of the circle, which is 2 pi times r. So then V perp is equal to 2 pi r over t, which is the period. So now r is equal to m times 2 pi r over t. The r's cancel. T is equal to 2 pi m. I'm forgetting something, over b. Over qb. Okay, now we've derived the period. So this is the period of the helix. But then what we need to know is that there's also an electric force. There's an Fe equal to Q times E, which is equal to Q E I hat. So what we want to know is, now we can apply kinematics. So x of t is equal to the initial x plus the initial velocity of x, Vx times t. So this is actually going to be big. Okay. The position of x, or here, wait. I think what we want to say is, yeah, the position of in the x direction at time 1 period equal to big T is the initial x plus the velocity in the x direction times t, which is 1 period, plus 1/2 times the acceleration in the x direction times capital T squared. And this is just the kinematics equation. Now, what is the acceleration, though? We have the force, so this is going to be equal to m times a. So the acceleration is going to be equal to q, the charge, times the magnitude of the electric field, you know, I hat, over the mass. So we can plug that in. So then this goes to 0. The initial position we can just say is 0, chosen. And we get Vx, which is just Vx. So Vx times 2 pi m over the charge times the magnetic field magnitude plus 1/2 times q e I hat over m times the period squared, 2 pi m over qb squared. And that's kind of as much as I want to do, but I'm pretty sure that's it. All right, so let's do this. Let's write this out. All right, let's see if I can do this from memory. Okay, charge Q with V initial equal to Vx, Vy, Vz. B vac equal to minus B K hat, E vac equal to E I hat. Let's do this, separate it out. Okay, find the displacement in the x direction after 1 period of the helix. Okay, so sketch, find t period to apply kinematics. Because acceleration is constant. So what are we doing here? We're okay. So first, so A, find to get T, find the magnetic force, apply the mv squared over r equation for circular motion to get r, the radius r, then use the fact that the velocity in this direction must be constant since magnetic force does no work. The velocity, use the fact the velocity in the plane of the helix must have constant magnitude. Use the fact that the velocity in the plane to find that, to assert that the velocity times the period is equal to the circumference of the helix in the plane. So, V perp times T is equal to 2 pi r. So then apply this back to the F equals ma, F equals mv2 over r, and solve for T. So, you get so FB ends up being QBV perp is equal to MV perp 2 over R. So R is equal to MV perp over QB. Then sub in the perp equal to 2 pi r over t, and solve. Okay, t is equal to 2 pi m over qb. So we have the period. Now we just say x of t is equal to x0 plus vx t plus 1/2 a t2. T goes to t, but what is a? F equal you're gonna get x0. This is also actually an I hat. Or, this is VX I hat. Where did I say that? I don't think I said that. Uh, okay. That one's not that bad. Let's see, what can I write about this? This is you know, uh helical motion period plus kinematics. It's like a 2 out of 5. That's like pretty easy. All right, 58. Okay, this one, all right, it's time to work through these. I really don't know if this is going to be on the exam because he's barely covered this. He'll probably cover this more in lecture today. But this stuff is really weird. Oh, yeah, this stuff is really weird because, in Faraday's law, you're taking this flux. The time derivative of the flux. But here's the thing. That flux, you can have the surface itself change. Which actually I don't fully buy. Like, how come you shouldn't be allowed to change the surface? I think probably what that is a little trick to get around the fact that, like, no, like, why can you do that? That doesn't make sense. All right, let's work through this one. 58. All right. I'm not still on mute, am I? Test? All right, good. So, all right, refer to the diagram. A conducting rod slides down an inclined plane that makes an angle theta with respect to the horizontal. There's a uniform external magnetic field that is vertically upward everywhere. The conducting rod is always in contact with the two sides of the plane such that a complete circuit is formed that has resistance R. The contact length of the sliding rod is given as L. There is no friction between the rod and the plane. There is gravity. By any valid method, find the terminal velocity of the rod as it slides down the ramp. Whoa. Recall that the equation for the motional EMF is given by B L V. But be careful about exactly what magnetic field you use. Assume the magnetic field created by any induced current is negligible compared to the external magnetic field. The terminal velocity? Let's see, do I have my notes here? If I don't have my notes here, I'm just going to read the solution. Motional EMF. Magnetic flux depends on three factors: the strength of the magnetic field, the area through which the field lines pass, and the orientation of the field with the surface area. If any of these quantities varies, the corresponding variation in magnetic flux occurs. So far, we've only considered flux changes due to a changing field. Now we look at another possibility: a changing area through which the field lines pass, including a change in the orientation in the area. Two examples of this type of... Okay, in part A, the flux through the rectangular loop increases as it moves into the magnetic field. In part B, the flux through the rotating coil varies with the angle theta. It's interesting to note that what we perceive as the cause of a particular flux change actually depends on the frame of reference we choose. If you are at rest relative to the moving coils in B, you would see the flux vary because of a changing magnetic field. In part A, the field moves from left to right in your reference frame. And in part In part A, the field moves from left to right in your reference frame. Yeah, if you are at rest relative to the moving coils. However, reference frame questions related to magnetic flux are beyond the level of this textbook. We'll avoid such complexities by always working in a frame at rest relative to the laboratory and explain flux variations as due either a changing field or a changing area. Now let's look at a conducting rod pulled in a circuit. Changing magnetic flux. The area enclosed by the circuit MNOP, okay, of figure 942 is I times, or X times L. Oh, that's an L. LX, okay. And is perpendicular to the magnetic field. So we can simplify the integration of the flux to just multiplication of the area. Yeah, so it's BLX, okay. Since B and L are constant and the velocity of the rod is dx dt, what happens if I click on this? Does it take me somewhere? Okay, yeah, it just takes me somewhere. We can now restate Faraday's law for the magnitude of the EMF I guess here's a question. If I'm in a uniform B field and I pull a conducting rod to the direction of the field, then there will be a magnetic force. But what if it's a dielectric rod? If you move any rod with velocity v through a magnetic field B, each charge in the rod feels, Q v cross B. So when the rod moves through the field, electrons get pushed sideways by Q v cross B. The charge separates across the rod, and this creates an internal electric field. Eventually, equilibrium is reached when electric and magnetic forces balance. So there can still be an induced internal electric effect, but it's not the same as a... Okay. The magnetic field does not automatically exert some large bulk force on the entire neutral rod just because it is moving sideways. Okay, that's cool. That's pretty cool. I don't really know what this I don't really know what an EMF is, I feel like. Like what is that? What is an EMF? EMF is best thought of as how much push... What? How much push per unit charge drives charge around a circuit? If some mechanism moves charge around a loop, then the EMF is the work done on the charge per charge. Changing magnetic flux. A changing magnetic flux can provide EMF by induction. Okay. Alright, so let's try to understand the equation then. V cross B. Okay, so positive charge is going to want to go this way. But is it really going to loop like this? Like, why doesn't it just separate to both poles and then both the top and the bottom and then just stay like that? All right, let's actually read this thing. Okay. All right, here we go. So the magnetic flux, all right, it's, flux M is equal to BLX. Since B and L are constant, the velocity of the rod is V is equal to dx dt. We can now restate Faraday's law for the magnitude of the EMF. Oh, I see. Okay. The current induced in the circuit is the EMF divided by the resistance by Ohm's law. The direction of the induced EMF satisfies Lenz's law. Wait. Wait, I'm confused. I thought Lenz's law was like, if we... Okay, wait, here we go. What is the change? What is the direction of the change of the magnetic flux? If we go this way, then it's increasing. B is increasing, which means... Or not B, the flux B, the magnetic flux is increasing. And we want to oppose the change. So if we push current this way, we're opposing the change. I got it. Okay, we're opposing the change. That's what we do. Okay. All right. So we're pulling this part of the circuit to the right. Okay. All right. The only thing that's really getting me now is the fact that why does the charge actually flow through the resistor? Because here, if you have a velocity this way and like... I mean, I think you just have to take it, that this thing is actually producing a volt. You can't say voltage, but an electromotive force. I don't think you can say voltage because um, the reason you can't say voltage here is okay, wait, let's see. The reason we can't really talk about voltage in these problems is because the force when the magnetic flux is non-zero means that it becomes non-conservative, which means that in a conservative force, which means there is path dependence. I think equivalently that not all closed loops are zero. Closed loop line integrals are zero. So the reason we can't talk about voltages in these problems is because, and the notion, the concept of a potential only applies to conservative forces. Because voltage is an electrical potential. When the electric field is induced by a changing magnetic flux, the electric field is generally non-conservative. And therefore, you cannot define a single value global scalar potential whose difference between 2 points gives all of the work done. Furthermore, the direction of the induced EMF satisfies Lenz's law. You can figure that. All right. This calculation of motionally induced EMF is not restricted to a rod moving on conducting rails. With F is equal to QV cross B as the starting point. Let's read that in words. The magnetic force is equal to the charge value times the velocity of the charge cross product with the magnetic field. As the starting point, it can be shown that the EMF, electromotive force epsilon, is equal to the negative time derivative of the magnetic flux holds for any change in flux that is caused by the motion of a conductor. We saw in Faraday's law that the EMF induced by a time-varying magnetic field obeys the same relationship. Okay, let's think about that. So imagine that this loop is fixed, but B is increasing. Then the same thing would happen. So Faraday's law holds for all flux changes, whether they are produced by a changing magnetic field, by motion, or a combination of the two. Good. So yeah, if we were increasing B, then the flux would be increasing, and then there would be a current. So, okay, now I'm ready to ask my question. The key jump is the moving rod is acting like a battery. That is why current through the resistor is not just allowed but expected. Inside the moving rod, every charge is moving sideways with the rod at speed v. In the magnetic field, each charge feels the magnetic force. So V cross B points up for positive charge. So positive charge is pushed towards the top, negative towards the bottom. That part you already get. Why doesn't it just stop there? If the rod were isolated, it would mostly stop there after enough charge separation is built up. The internal electric field would grow until it balances the magnetic push on the charge. That would give a static charge separation and no sustained current. But here the rod is not isolated, it's part of a closed conducting loop. So the charges that get pushed to the top of the rod do not stay there. They can flow across the top rail, down the resistor. Okay. Then inside the rod, the magnetic forces push them up again. Oh. Okay, all right. It's starting to click, actually. It's very, very weird, though. Dude, Faraday's law is by far the coolest of the Maxwell's equations. So we're going to have a magnetic field. Faraday's law of induction describes how a changing magnetic field can induce an electric current in a circuit. All right, I think I'm ready to start doing this problem. Okay, so first we're gonna say what is the terminal velocity, man. All right, let's start to figure this out. I induced. Okay. All right, I don't want to read the problem. I just want to start doing some stuff. Okay, B. All right, so let's do I, J, and then K hat, standard reference frame. So then the magnetic field is given by J hat. So B vec is equal to B J hat. Okay. Then the mass of the bar needs to be given, right? Okay, we have an angle theta. This is length L. Does this thing not have to have a mass? Or are we given its velocity? Let's see. Because I was a conducting rod slides down an inclined plane that makes an angle theta with respect to the horizontal. There's a uniform B field up. The conducting rod is always in contact with the sides. Resistance R. Circuit has resistance R. The contact length of the sliding rod is given as L. There's no friction. There is gravity. By any valid method, find the terminal velocity of the rod as it slides in the ramp. Recall that the equation for the motional EMF is given as the BLV. Because what is the flux? The flux is going to be BLX and then dx dt, because it's going to be the EMF is the because EMF epsilon is equal to the minus d magnetic flux dt. So the IB is going to be equal to, or bro, why am I saying IB? Magnetic flux is going to be B times A is equal to B times L times X. But then d flux dt will be, since the magnetic field is not changing and the length is not changing, it's going to be BL dx dt is equal to BLV. So then epsilon should be minus BLV, right? Or is it positive? Okay, so there's not a minus sign here. Oh yeah, because Wait, what? Oh no, it does have a minus sign. What the hell? Why did he say yes? Okay. Um. All right. So let's keep with the sign thing, and then. But the flux is this area projected down, so it's actually going to be times cos, times cos theta, because BL, um, yeah, but what does that minus sign mean? Which way is the current going to go? We have B up, and then we have V, let's just say down. Wait, V has a component, Vx. So V cross B, the force is out of the page. V cross B, it's pointing towards me, which means that current is going to flow this way to oppose the change, because see, we have this surface and it's getting bigger, the magnetic flux is getting bigger, and we want to decrease that magnetic flux. So if we make a current spin this way, then then there's going to be an induced magnetic field, or there's going to be a magnetic field by that current that opposes it. Man, this problem seems hard, dude. Yeah, exactly. Yo, I see you. Len's law, bro. Len's law. But I'm still trying to intuit these things. You got to say them out loud like 100 times before you really understand what's happening. Okay, but now we need to find the terminal velocity. Okay, B perpendicular is equal to B cos theta. That's what I got. So EMF, so yes. Okay, the EMF is, yeah, BLV cos theta. I got a minus sign there. Oh, interesting. Okay, I didn't. Okay, by Lenz's law, the induced current is out of the paper. Wait, but actually, I is out. Okay, from here, I is out. Yeah, okay, that's fine. I understand that. This would create a B induced opposite to B external to oppose the increasing flux. Yeah, I'm not going to do the differential equation. There's definitely a way to do this without the differential equation. I could do that, but I don't want to do that. All right, because the area is increasing here. So the force, the magnetic force, yeah, IL cross B. But I did. Let's see. I guess I didn't. Well, because I was going to do QV cross B, but I guess here that doesn't actually make sense because we have no idea how much charge is really going on here. So you can't use this. So yeah, so you have to do, DFB is equal to I DL cross B. But L is given, right? Because what are we trying to find the force on? The magnetic. Oh, I see. All right, we're trying to find the force of the external magnetic field on the rod. But why? Why find FB on rod? At terminal velocity, V what is that? VT. Oh, okay. Terminal velocity VT. Acceleration 0. So F equals ma system rod 0. So we have, yeah, the magnetic force, the normal force, and what is this? What is this force here? That's got to be the... No, because I think he said, assume the magnetic field created by any induced current is negligible. So that's not what that is. So what is Fs? Oh, is this G? This might be gravity. Oh, here we go. Yeah, Fg. All right, Fn, Fb. IDL cross B. Is that right? Let's imagine it's going the other way. IDL cross B. All right, so it's going that way. Yeah. Okay, so the magnetic force is going to my left. There's a gravity force and a normal force. How does he find the gravity force, though? That's what I don't understand. And he introduced M, but there's no M in the problem. Okay, so we assume that the rod has mass M because there's literally no other way to do the problem. I don't know why I was hung up on that. Okay, so that means, yeah, let's draw the free body diagram. FB, FG, and F normal. Okay, so now we have this thing on this triangle here. This is a theta. I always hate these things. This is perpendicular. So how the freak do we do this again? Okay, this is a similar triangle. This is theta. Okay, so FG is equal to minus mg j hat. FB is equal to I L cross B. L, this stuff is out of the page. So this is let's do I, J. Let's just take the determinant really quick. B is j hat, so we're going to get 0, 0, I, L, 0, B, 0. Okay, so now, yes. Okay, so FB is equal to minus I hat times minus ILB. So that's the magnetic force on the rod. Okay. Now the magnetic force on the rod, yes, it's in the minus I hat direction. FG Dude, I'm so bad at the geometry, the inclined plane problem. If this is theta, what is this angle? This is a right angle. This is theta, then this is phi, which is the... So that's theta. So wait, hold on. We don't have the FG. Wait, actually, FG is. Wait, FGX minus FBX is equal to 0? MG sine theta minus FB cos theta. Okay, wait. So FG sine theta minus FB cos theta. Did I get that right? Okay, I think I see that now. And then MG sine theta. This is the normal force? What is that? Oh, wait, no. No, yeah, mg sine theta minus fb cos theta is equal to 0. And here's the application of Ohm's law. No, I didn't. I just did that with the yeah. So what you got to do, dude, this guy in the chat is kind of goated. What you got to do is you got to draw the let's see, come on, load. All right, so let's just do this. So we have triangle with a theta, and what you got to do is turn it into. Let's see, this is gonna be. Actually, wait, I have an idea. Instead of this, I do. Is this a select tool? Okay, yeah, copy this. Drag it over here, and then I think I can rotate it. Can't I rotate this thing? I'm pretty sure that I can rotate this thing. Okay, it's kind of like this. And so now we have Fn, the normal force. Then we have like FB. This is B. Actually, wait, let's do this. B, or FB. And then a line here. Oh. Parallel to this one. And this is FG. This is FG. So then you can see here, if this is theta, then, and we call this phi, and this is 90, then this is theta, and this is phi. But the thing that I'm Wait, hold on. I'm going to reorient. So, all right. So that's what you do. Then the answer though is that since we have phi here and theta here, FB. Oh, I'm still having a hard time seeing that. This is the hypotenuse. Yeah, so cos theta, cos phi. Cos phi is the same as sine theta. So FB cos theta plus FG cos phi sine theta. So FB cos theta plus FG sine. So let's just do this. Cos or sine theta is equal to 0. And I guess he doesn't like do the rest of this thing. Because like what I would imagine is if we have this mass here, mass M, then there's a force. So then Fg is equal to minus mg j hat downwards. There's just a force going down there. But the magnitude of the normal force has to be less than the magnitude of the gravity force, right? Okay, wait, let me just figure this. Wait, oh fuck, why did I do that? The force of gravity. Oh, it knew exactly what I wanted. Parallel to plane. The force parallel to the plane is mg sine theta, and perpendicular to plane is mg cos theta, because parallel to plane and perpendicular. The perpendicular to plane is this. Oh yeah, which is the same as this. Okay. So yeah, cos theta is perpendicular to the plane. You knew exactly what I wanted, bro. All right. That's pretty good stuff. So now I want to do this thing with all vectors. That's the best thing. All right, let's do it. So all right, so we have I'm going to keep it in the original coordinate frame. I don't want to change coordinates. So FG is equal to 0 minus mg 0. FB, so then, oh wait, yeah. So FB is equal to, let's just say, the vector, we'll just keep it as a magnitude. It's going to be minus FB 0, 0. Oh yeah. Okay, wait, I actually have to lock in on these problems because there's another one on the homework set from set 7. No, it's this one. And to solve it, yeah, you have to just say let Fn's magnitude be n, and then you do the rest of it. Like, why is it? Why is it? Oh yeah, wait here. This is actually the best way to do it. When theta equals 0, when theta is equal to 0, the Fn is j hat. Cosine of theta is equal to 0, or sine of 0 is equal to 0. Therefore, Fn I hat is equal to, n sine theta. Okay, I got it. That's the best way to do it, is just to plug in some numbers. So Fn is going to be equal to n sine theta and cos theta 0. Okay, so now we have our equations. All right, let me just jot them down so that we have something. All right, I'll do the full thing later, but I just want to write this down. So Fg is going to be equal to 0 minus mg 0. Fb, we're just going to call this Fb. So this is the vec 0 0. And then the normal force Fn, it's going to be n Fn sine theta Fn cos theta 0. The best way to see this is to skip the geometry and just imagine the direction of the normal force when theta is 0. That's the best way to do it, man. Otherwise, you're just like, oh, wait, hold on. I'm getting a phone call. I'll be back in a second. All right, I'm back. Sorry about that. All right, so let's lock in here. So, okay, so the normal force, yeah, the best way to see this. Okay, so now we basically just solve, um, um, wait, why did I write minus FB? Oh, because it's directed. Yeah, okay, so minus FB plus N sine theta is equal to 0. And then minus mg plus n cos theta is equal to 0. And then you can use this to just solve for the normal force. But I guess my question is, we're solving for the velocity. Okay, what do we have right now? We have the electromotive force, which is, yeah, LBV cos theta. And then once you have, I'm probably gonna say voltage, but voltage is not really what you want to see. Yeah, bro, I should never have taken that phone call. Lost all my views, bro. Lost all my views. It's flattened out immediately. Okay, let's do this thing. All right, so we know the force. We know the magnetic force is going to be IL cross B. I think we found though, it since L is K hat. Let's see, where's my determinant? Yeah, L is K hat and B is J hat. Yeah, we got, yeah, FB is equal to minus I hat ILB. Then, but we don't know what I is. This is the current. And so the current is actually I is equal to the electromotive force over, V equals IR over the resistance R. And we're given the R. Okay, so what is our electromotive force? Okay, here we go. So FB is actually I hat. Wait, no, but I got a minus in the BLV. All right, we're going to have to track the minus signs very carefully. But let's just go with it. So I had BLV cos theta, B squared L squared cos theta over R. Okay, good. So we have the magnetic force. So we're at I induced terminal velocity. Okay, this is definitely one I want to do again. Let's keep moving on. So yeah, so this is so this is the, I would say probably this is like the classic motional EMF problem. Do it again. Got to do it again. All right, 65. Find the magnitude of the magnetic field at the center of a square of current I with side length A. Your final answer is an integral ready to integrate. Use a full vector treatment at least once. Okay. So this is literally it. This is so chill. 65. Let's make sure that I got the right thing. Okay. So square side A current I point P origin point P origin square side length A current I center P. Okay, find B of P. Okay, so this is gonna be a Biot-Savart problem. Okay, so let's do this thing. So Biot-Savart, you have a square. Okay, we have P, we have I going, so it's gonna go like this. So by two steps, so two-step right-hand rule, B is gonna be into the page. This is I, this is length A. B of P equals what? All right, so here's what I'm gonna do. I am going to take a IDL here. So we're going to call this IDL. Then we're going to have an R hat, which is our vector. And so, Biot-Savart. So we're going to have B, the magnetic field is equal to the integral of the little contributions by the principle of superposition. So 1, 2, 3, 4. So this thing, if I have a current going down here and I have it going down here, then this is going to be the dB. Wait, is that right? This goes down, then R hat goes across. This is down, and I turn. Wait, actually, let's do this IDL. So we go up. Oh, I hate doing this. For some reason, just totally messes with me. Because I feel like I get the same thing. Because if I go like... You have to start with your hand flat, I think. You go like this, then I curl it to this way. Why am I tripping out? Let's do a simpler problem. It's just going to be a line with a point. The current is going here, I, with a length len A. This is P at the origin. And IDL. We have the R hat. Okay, so I'm going to my right. I'm going right this way. This has to be a plus K hat. But is it only plus K hat? You actually don't even need to think about the angles. I don't even know what I'm doing. All right, so let's make this the true IDL. This is the one. So this point here is going to be minus A over 2 minus A over 2, 0. So we're going to make the coordinate system I hat up to the right, J hat up, k hat out of the page. Now, so let's just do the integral around 3, and then we're gonna figure out what that looks like, and then we'll continue from there. All right, so all right, okay, so first off, dB is going to be mu 0 over 4 pi times IDL cross B hat, or B, so wait, cross R vector over R cubed. All right, that's easy enough. So the line traced out by the bottom is going to be minus, is going to be 0, no, it's going to be x minus a over 2, 0. This is the line 3 trace. So this is L of x. Then to find R is going to be equal to P minus L of x equal to minus x a over 2, 0. The norm, R, is going to be x squared plus a squared over 4 square rooted. Okay, so we're almost ready to evaluate the integral. dl, we need to find dl. dl dx is equal to just 1, 0, 1, 0, 0. So it's just going to be dl is equal to dx I hat. And I think actually for a lot of these you kind of can skip it, but I always end up just evaluating it. All right, so let's go ahead. Mu 0 over 4 pi integral, and this is going to be from minus a over 2 to a over 2. And then it's going to be I dx. Oh, wait, we need to take the cross product. What am I doing? I, j, k. So R vector is going to be minus x, a over 2, 0. And then dl, IDL is I dx, 0, 0. Okay, so I is going to have 0. J is going to have 0. It's purely in the k hat. So it's k hat times minus I dx a over 2. Okay, so now we have the cross product. So that's going to be minus I dx times a over, so let's move the 2 out here, or 2r cubed. Now R is dependent on this. So this is going to be equal to, and it's k hat. So no matter where we do this thing, it's, oh wait, and I forgot to say, yeah, k hat. So it's always minus k hat. I don't know what I was tripping on earlier, trying to like draw. This is not where dB is. dB is not in the plane of this at all. A better way to think about this is like, if you just look at the two vectors and you know the cross product has to be perpendicular to the plane defined by the two vectors, then there's no way I could have drawn it like this. So oh yeah, but this is counter to the, yeah, this is counter. The I is really going this way. Okay. Gotta get my diagrams right. So I imagine though that it is just going to be 4 times this. So let's do this. It's going to be minus k hat mu 0, times 4. Okay. Over pi, 2 pi I a. A is not part of the integral. Okay, integral from minus a over 2 to a over 2 of dx over x squared plus a squared over 4 to the 3 halves. All right, let me just write down my answer, and then we'll see if I'm right. So I got minus k hat mu 0 IA over 2 pi integral from minus a over 2 dx over x2 plus a2 over 4 to the 3 halves. Let's see. He didn't get he just took the magnitude, but I'm pretty sure it's minus k hat. All right, mu 0 IA over 2 pi. Okay, cool. It actually isn't that bad. The only thing is, let's say, okay, notes. Only thing is to make sure we sanity check our dB vectors. Always ensure that the cross product of IDL and R hat is perpendicular to the plane of the vectors. Because it's easy to draw. It's on.
It's on?
Yeah. So,
It's on?
yeah, here.
It's on. I want to suck your blood.
Class in 10 minutes.
Do you want another bagel?
Yeah, let me come. Oh, yeah, you want to just toast it?
Yeah, I can make you something. Do you want a sandwich?
Uh,
do you want the egg and cheese and stuff on the bagel?
No, I think I just want cream cheese.
Okay.
Okay, so, yeah, so I think this problem actually, I thought it wasn't easy, but it's a. I would just say straightforward Biot-Savart problem. All right, 97. These ones that are like high up there, they're difficult, or they're like new info. But I'm gonna have to end the stream in like 5 minutes. I'm gonna be back on like right after my class though. Like we're doing physics all day, every day until this exam. This exam is not gonna stop me. All right, okay, let's see. Here we go. All right, so it's definitely one of these motional EMF problems, but there's an acceleration here. That's kind of interesting. All right, so let's 97. Okay, see the diagram. A conducting rod of length L and mass M is accelerated from rest a distance d along a circuit. The acceleration is given as A. The combination of forces to cause the acceleration is not what this problem is about. The rod is connected to a fixed circuit with resistance R. A uniform B field everywhere perpendicular into the page. Find the total charge Q that passes through the resistor by the time the rod has traveled through the distance D. Oh. Okay, so BLV, motional EMF. So V. Oh, wow. Wait, but you're going to have to use BLV is not going to do it. Because actually, what you can do. Wait. Yo, I don't want to see the solution. I don't want to see the solution. I want to know this thing. All right. So it started from rest. So initially, there is no electromotive force across this thing. Let's also figure out. Oh, I never actually looked into the minus sign on the ramp problem. Let me write a reminder for that one. Was that this? No. This is some random one. Classical motional EMF 58. To do. Look into the minus sign on the motional EMF. Is it EPS is equal to minus BLV or BLV? Because the correct one is definitely the minus. I'm almost positive. Okay, so let's just remember to do that. I guess we're going to have to come back to it when we solve this problem. But let's just think through it. So what is happening to the flux? So I guess we have to pick we have to pick a normal for the area. Yes, we have to pick a normal for the area. Okay, so let's just make the normal. So what problem is this? 97 or something? Yeah, okay. So 97. Have to pick a normal. Oh wait, shit, I have to get to class. Okay, let's think through this. So let's just take it to be minus k hat, parallel to the B field. So then the magnetic flux at t equal to 0 will be B L D. Oh, it's coming together. But what happens? So then D flux, the change in magnetic flux with respect to time is going to be BL V. V is dx dt. But we don't know the velocity. We only know the acceleration. So V of t is equal to V0 plus AT squared, right? AT. It's just AT. Yeah. All right. So the initial velocity is 0 and the A is given. So we know the velocity. So then we know the flux. Okay. The problem is like kind of. So, but then once you know and I'm pretty sure the EMF will be time dependent. So you have to integrate or what? Yeah, you have to integrate. That's what I thought. Okay. The problem makes sense. I got to get to class. Well, I'll be back. I'll be back in like 1 hour.